In the third part of this first lecture series on statistics, we're going to be thinking now about conditional dependence. So at this point, we're actually moving on to bivariate relationships, or relationships that actually involve two variables. So first, we're going to introduce a bit of the theory and then talk a little bit about the statistics that can be used to test the theory. So the idea of conditional dependence is pretty much the idea that if you can measure sort of one thing out in the world, you might be able to know something about other things out in the world. So suppose we want to know whether or not it's rain. And if it's cloudy, then there's a 70% chance of rain. But if it's sunny, then there's only a 20% chance of rain. So in other words, we've measured two variables here, whether it's cloudy and sunny, and whether or not it rains. And the chances of whether or not it's going to rain, in fact, depend on whether or not it's cloudy or sunny. So this is basically captures the underlying conceptual essence behind the notion of conditional dependence. It means that one type of characteristic of the world, of a variable that we've measured, depends on another one. Now, if we were in England, we might not actually see this type of conditional dependence because the chances that it's going to rain are about 80% regardless of whether or not it's cloudy or sunny, right? Because the weather can always change within an hour. So that would be conditional independence. The idea that whether or not one thing happens, our I guess y variable or our outcome variable, whether or not it's going to rain, is actually independent. It means it's the same regardless of the initial state, whether it's cloudy or sunny. So formally, what we see is that, and this might have been something you've seen before, the probability of some outcome B, right, conditional on, that's what the line means, A, is just the probability of A times the probability of B. So in the case of England, what you can see is that in essence, the probability of whether or not it's going to rain times the probability that it's cloudy is different in England and in Amherst. And they just aren't equal. You can go through and do the math, but basically this is the way you calculate whether or not you have conditional independence or not. It should be that the probability of these outcomes isn't dependent. So what's really nice about this definition is it actually sets up a statistical test that we can start thinking about if we think about a contingency table, rainy by cloudy. So suppose we see something like this. Can we actually calculate whether or not it's independent of the variable sunny cloudy? So you can think about this for a little bit and pause the tape, sort of think about how you would actually go through and calculate whether or not basically the things that you observe in these cells correspond. I mean, you have an intuition that it's not right, but think about how you would actually calculate it. Okay, assuming you have returned now from the pause, let's take a closer look at what we do in the statistical world. So basically what we can do is set up a set of equations where what we expect, as you can see, there's a 50% chance of it being cloudy, a 50% chance of it being sunny. We're looking at these marginal things, a 9 out of 20 chance that it rains, 11 out of 20 chance that it doesn't. So we can use our earlier equation of independence and actually do the calculations and figure out that there should basically be 45 days, if we assume we have 200 days overall, 45 days where it rains, 55 days where it doesn't, in both of the top and the bottom. So that's just basically our expectations if things were independent. These are the number of days we would expect it to be cloudy versus rainy. What's nice about that is that we can then actually go through and see the actual number of days, which is the first number, minus the expected number of days, which is the second number, and calculate how many days are not according to expectations. So we should expect the sum of the squared differences to be close to 0. But if it's not, then we think, okay, that means that there's that maybe things are not independent. So what we can end up then with is something called a chi-squared test. So this is just simply the chi-squared statistic is calculated as exactly the way we just did it, the observed minus expected squared, divided by the actual number that we expected there, and then you sum up all up for each of the 4 boxes. So again, looking back, we would basically subtract 70 minus 45, 30 minus 55, 20 minus 45, square those, divide it by the expectation, which is like 45, 55, 45, and sum up those numbers. And that will give us our chi-squared statistic, which we can then actually look up in a chi-squared distribution table using the degrees of freedom as indicated. So in this case, we can now answer the question, does the chance of rain depend on whether or not it's cloudy? We see that we have a chi-squared statistic of 50.5 with 1 degree of freedom and n equals 200, which corresponds to, it's basically the statistic that you calculate is about a 7.9, and our probability is very, very low, which basically means those things are not very likely to be conditionally independent. So there's almost no chance at all that cloudy is independent of rainy, and we can safely conclude that the chance of whether or not rain depends in a statistical sense on whether or not the sky is cloudy. So again, we can really mostly conclude that there's almost no chance that cloudy is independent of rainy, but you can certainly say, right, that it depends in a statistical sense on the other. So we can do the same type of thing here with internet news. So this is the variable we were looking at earlier in the lecture series, and go through and actually do the calculations. You can see I've greened out the ones that are higher than expected, redded the ones that are lower than expected, or maybe it's vice versa. No, sorry, it's vice versa. Red is the ones that are higher than expected. Green is the ones that are lower than expected. And you can go through and calculate that out and find that you have a chi-square of 95.76, 7 degrees of freedom. Look it up in a chi-square table just as indicated and find out that it is well over not just the 0.05 but the 0.005, right? So this is very much the case that these are not conditionally independent. In other words, we believe that American men consume internet news on more days each week than American women. Again, because we've got this nice ratio variable, it's easier to conclude that. Okay, so that's one way to compare two groups, but as we could see from the news case, it was pretty bulky to have to go through. There were lots of categories, plus it's a ratio variable, so maybe that's not the best way to calculate it. So how else can we tell whether or not two groups are different? Now we're going to talk a little about using the t-test that was introduced earlier to think about null hypotheses to instead compare two groups. So here what we do is instead of, as we did earlier, where we had H alt minus H null, now we're going to have basically the x's are going to be x for the men's group and the mean for the women's group. Again, we're going to subtract them from each other. There are some different assumptions that one has to make about how you actually deal with what the standard error is when you have two groups. Do you treat it as a standard of the whole group? Do you do some other things? I'm not going to get much into that. If you're taking a formal statistics class, you do need to know those things. But for now, basically you can stick with the idea that there's a standard error that in this case actually does seem to be about the same for both groups. You calculate your t-statistic, and we're going to then be able to basically interpret it exactly as we did before. So here we have a t of 9.12. What do we know? That means as long as it's over 2, the difference is significant, right? So we can safely conclude that the mean of men is not the same as the mean of women. And in fact, it's well outside that 95% confidence interval of plus or minus approximately 2. We'll come back to the assignment whenever we're in class, but that is the conclusion, or at least an introduction of some basic descriptive statistics and also some basic univariate and bivariate inference.